Hello, I'm P.S. Sastry. I plan to introduce robot kinematics through a few lessons or lectures. The topics I plan to cover are degrees of freedom, configurations, rotation matrix, basic rotations, translation, and homogeneous transformation matrix, RPY, ILR, and other rotation representations. The Danovet-Hartenberg convention, link parameters, velocity kinematics, Jacobian, inverse kinematics. Some of this terminology as we go through the lessons, they'll become clear to you. Well, to start with a robot, we have a schematic representation here. Robot is an open kinematic chain. At the open end, you got a end effector or a gripper. And basically in a robot, we like to keep track of the position and orientation, velocity, etc. of the end effector with reference to a base frame that is some kind of inertial frame which is fixed so that we have an idea where this is end point is. The robot consists of a series of links connected by joints. These joints can be rotary or prismatic. That is rotary in the sense they produce relative rotational motion between adjacent links, or the two links can be moving linearly. Each of these joints are driven by some kind of actuators, usually controlled by a central computer, and they can be electrical, hydraulic, pneumatic, etc. And in kinematics, we'll be mainly interested in finding the velocity and position, orientation, and velocity of the end effector, or it could be any point within this on the robot arm. But accelerations, of course, they'll be useful mainly for finding out the joint torques or the forces to be exerted by the actuators. And in these lessons, we'll not worry too much about these accelerations. Concerning the degrees of freedom, robot to be able to position an object held by the end gripper at any point within the workspace, that the extent of space volume that the end effector can go to, that's called the workspace. Within that, going there and also being able to orient the frame attached, any object it is holding, or actually what we do is we say instead of object, a rigid object, we attach a frame to the end effector. And so we try to talk about the orientation of the frame. So the orientation of the frame and look at position of the origin of the frame. So that will need, if you want to describe it uniquely, it will need 6 degrees of freedom. So, but on the robot, at each of these joints, we provide only 1 degree of freedom. The human hand, for example, has got 3 degrees of freedom at the shoulder, 2 at the elbow, 2 at the wrist. So 7 degrees of freedom in all. But then the shoulder itself has got 3 degrees of freedom. But then the complex controls at the shoulder are very complex. We don't make it so complex. We have only 1 degree of freedom in the robots at each of the joints. Therefore, for providing 6 degrees of freedom, we need 6 joints. Well, some robots may need more, where they have to go through some restricted spaces, etc. They may need more than 6 degrees of freedom. And some of the pick and place type of robots need less, 3 or 4 degrees of freedom will be adequate. So we already covered that. Yeah, one more thing is the first 3 links provide are so designed to provide the necessary workspace, the space of the reach of the robot. And the last 3 joints are normally three very compactly made rotary joints called the wrist. They're more catered towards providing the kind of orientation required at any point in the trajectory of the robot manipulator. So again, the some terminology, the forward kinematics, finding out the position and orientation of the end effector given the joint variables, given the angle of rotation or displacement of the joints, for the joints. If you want to know the position and orientation of the end effector, that is called the forward kinematics problem. On the other hand, many times you know where the end effector has to go to. It has to trace certain path and all that. Then what should be the corresponding joint variables? What should be the positions of the various joints for the end effector to be at that position at that point of time? This problem of finding out the joint variables given the end effector position and orientation is called inverse kinematics. Similarly, velocity kinematics, given the velocities of the joints, what should be the velocity vector? What will be the velocity vector at the end point? It's a 6 by 1 vector, and that is called the forward velocity kinematics. And again, more importantly, given the end point velocity vector, uh, what should be the velocities of the various joints at that instant of time? That is called the inverse velocity kinematics. Now, we have covered most of the terminology so far associated with the robots, so we can leave this, and then we'll look at the typical robotic system and its components. The robot system basically, the heart of this robot will be a central computer that will be giving signals to the various actuators being driven, and each of the joint has got an actuator. So the signals will be going from the directions will be going from the central computer to each of these actuators, depending upon what program is being executed, and in each program catering to a particular job being done by the robot arm. That program is executed, and that is based upon the program. The necessary instructions sent to the various actuators by the computer. So various programs may be stored depending upon the number of jobs, functions that this robot performs. Also, at the end of the robot, you got a gripper or a tool for a specified job. For, it may be for spray painting or arc welding. We have one type of tool held by the gripper, and we also have a power unit, of course, parallel. And then this teach pendant could be one part of the system. Teach pendant is one where you, particularly in pick and place type of operations, you operate this teach pendant so that the end effector will go to the particular position you want. And then the gripper operations and all are performed by the teach pendant. And these positions of these joint variables at that point are recorded, and then it is again taken physically to another point by operating various switches on this end of on this pendant, teach pendant, and then the positions at the point are also recorded. Later on, the various speeds are added for the travel in between, and then it is put in a suitable code as per the program instructions that this computer can handle. And then, so this is basically say, a device to teach. This is done offline. And of course, this is used for mainly pick and place type of operations. But for continuous path control, like spray painting, etc., probably an expert will run the endpoint, the gripper through the various motions. And then in the trajectory or the path, the times, mm, the positions, and therefore the velocities of the joints are all recorded. And when the path is completed by the expert, Later on, again, it's put back into the proper code, and then when it is run, the end effector will be doing just what the expert has done. That is one method of teaching. Okay, so these are some of the basic components of the uh, the robot manipulator. Now we may have to draw a few schematic diagrams before we go to further kinematic analysis. So in that, we'll have to look at what are the draw the various joints, and we'll have to know something about the workspaces also. The commonly employed schematic representations the uh, for a rotary joint are these. You got basically joint L1 and link L1 and L2. There is a axis about which this rotation theta happens, and so this is one schematic representation. These are similarly other schematic representations. The angle theta is shown here, and the prismatic joint, this is a linear motion D. It is D, and L1 and L2. They are separated. The two links move by this distance D, and this is the joint variable. In the case of prismatic joint, and other than that, we also call the arm part. We have an arm and a wrist. A wrist is usually made up of three rotary joints in a row, and that wrist is attached to the end of the schematically to the end of the first three links. For example, this is a Cartesian arm. It has got three consecutive prismatic joints: prismatic, and prismatic, and that means linear motion. This kind of a motion produced here, this kind of a motion, and this kind of a motion produced, and mm, it is called a Cartesian arm, and we call it PPP, prismatic. So the workspace corresponding to Cartesian arm is this. In the plan view, this is the motion of the end effector this way and this way. That is represented here. And in the elevation, this motion, vertical and this motion are represented here. And together, the two pictures, plan and elevation, constitute, gives information about the workspace possible. Similarly, for other configurations also, you got a cylindrical arm, actually a rotary prismatic chain of joints is called a cylindrical arm. And the workspace, if you look at the plan view, it can rotate so much, and maybe some 300 degrees around. And there's a vertical, this movement and this movement provide the elevation. Together they constitute the workspace for a cylindrical arm. The next one is a spherical arm, they call, and prismatic like this, and so rotary like this, and prismatic like this. And you can see the plan and elevation, and this is typically the spherical arm and workspace. Similarly, elbow is three rotary joints in a row, and this is typically the workspace. And the last one is the popular one in assembly operations. It's called SCARA, or Selective Compliance Assembly Robot Arm. It has all parallel axis. First two are rotary axis parallel to each other. Third one is again a vertical axis, but prismatic joint. And the last one is again rotary, and mainly for some kind of fixing bolts, etc. This can, or for drilling operations, this can be used for assembly, and mainly used for assembly operations. So these are some of the basic 4-5 or some of the basic configurations, for some of which we'll be looking at the velocity kinematics in the lessons to come.